Okay, so I'm just going to move into the maths of this last part here. I would suggest when I'm finished explaining this, you have a look at it yourself and see can you figure it out, because it's not that hard, but I know when I explained it all together, it seems a bit confusing. Okay, so I know the last class we were talking about the relationship here between frequency and length, frequency and tension, and frequency and mu. And then we have the two experiments that as soon as I get back we're going to do to determine or try to verify the relationship between frequency and length, and then separately between frequency and tension. But before that, we did work on vibrations on a stretched string. So we've seen this stretched string a few times. So this one at the top here is the this one here is the fundamental frequency. The next one then, oh yeah, do you remember this with the naming thing? So this is the fundamental frequency, or it can be called the first harmonic. Yeah, and that's where you have two nodes, so you can see them named here, two nodes and one antinode. Yeah. Then we move down, and if we're using the fundamental frequency, the red naming convention, then this is the first harmonic. No, it's not. Sorry. This is the first overtone. This is the second harmonic. Okay, and what this one looks like, you can see it here. Oh, I don't want to use it. So we've got 1, 2, 3 nodes and 2 antinodes, and you get that sort of infinity shape. And then down to the next one, if we're using fundamental frequency and overtones, then that's the second overtone. And if we're using harmonics, it's the third harmonic. And then what does the third harmonic look like? Pink. So we have 1, 2, 3, 4 nodes and 1, 2, 3 antinodes. Yeah? And then from there, do you remember we got the maths where we had like the distance from node to node, or node to adjacent node. So if you look, I don't know why, but let's look at this picture here. Like, that's a wavelength. Yeah, can you see what I'm doing there? That's a wavelength. So node to node, which is this bit, is half a wavelength. Yeah? And then if we do the distance from node to antinode, so again, if we concentrate on the same picture, that's a wavelength. So then node to node, like we said, is half a wavelength. So then node to antinode, which is just that bit, is a quarter of a wavelength. All right. So we learned all that way back when we were doing stationary waves for the first time. So we're going to use that knowledge, I suppose, down here. No, I kind of attempted to draw them. They're better up above, but anyway. And we're going to look here at harmonics or overtones in a pipe closed at one end. Okay? So this is actually, I don't know if you noticed, but the two experiments up above were sound 2 and 3. This is actually experiment sound 1. Okay, so what we use for this experiment is like a tube. Open at both ends. And then what we do is we put the tube into a container of water. So this is water. And that closes the pipe at one end. So you get this column of air here. And essentially what we do is we send a sound into it. We use a tuning fork to send a sound down into the pipe. The sound goes into the pipe. So you have the sound travelling down the pipe. It hits off the closed end. It reflects and it travels back up the pipe. So you have your incident wave going down. You have your reflected wave going back up. So essentially what you have is two waves meeting. When you have two waves meeting, you have interference. And then if we can get the conditions right, we can get constructive and destructive interference to set up in a pattern. And if it sets up in a pattern, we can get a standing wave. Okay, and that's what we're doing here. We're trying to set up standing waves in a pipe closed at one end. Okay, so standing waves in a string, like I showed you, your first harmonic looks like this. Oh, let's not correct that. Yeah. Your second harmonic then looks like that. Yeah. And then your third harmonic looks like that. Okay, so I've shown you all them up above. Now, it looks different in a pipe closed at one end. So in a pipe closed at one end, this is what the first harmonic or the fundamental frequency looks like. So down here, we get a node. And up here, we get an antinode. Yeah? Now, we just did the maths of this a second ago. So the distance from the node to the antinode is lambda over 4. So we can say that the length of that is lambda over 4. Yeah? I'm just going to do a little bit of maths here. So, you know this formula, C equals F lambda? So I'm going to rearrange this for lambda. So I'm going to multiply by 4 to cancel, and I'm going to multiply by 4 to balance. So I get lambda equals 4L. I'm going to put that in over in that formula. So I get C equals F times 4L. And then I want to isolate F. So I'm going to divide by 4L here, and I'm going to divide by 4L here. So I get F1, which is the frequency of the first harmonic, is C over 4L or a quarter C over L? Yeah? Okay, so we'll keep going. So that's what the first harmonic looks like. This is what the second harmonic looks like. So the second harmonic has two nodes. And it has two antinodes. The key with drawing these is that you must have a node at the closed end and an antinode at the open end. And if you follow that rule, you'll be able to draw them all. Yeah? Okay, so we're going to look at the length of this again. So I'm trying to get this length from top to bottom. I'm going to break it up, okay, because in here I have node to node, and up above the distance from node to node is lambda over 2, half a wavelength. And then here I have node to antinode, which is a quarter of a wavelength. So the length of this one is lambda over 2 plus lambda over 4. Now you can type this into your calculator. See how good your primary school fractions are, as literally a half plus a quarter. Yeah, and if you do that, you get 3/4. You just have to remember to put the lambda back in. So L is 3 lambda over 4. Yeah, okay, so same maths again. I'm going to take my wave formula, C equals F lambda. I'm going to sub, oh no I'm not, I'm going to rearrange this first. So I want to use yellow. I want to isolate lambda. So I'm going to multiply by 4 to get rid of my 4. So then I have 4L equals 3 lambda. And then I want to isolate my lambda. So I'm going to divide by 3, divide by 3. So I get lambda is 4L over 3. Now I'm going to sub that in there for lambda. Yeah? So I get C equals F times 4L over 3. And I want to, so I'm trying to be consistent with my colours somewhat. I want to isolate F again. So you go to the maths. We'll multiply by 3 to get rid of the 3. And multiply by 3 over here. So I get 3C equals F times 4L. And then again, I want my F. So I'm going to divide by 4L here. And I'm going to divide by 4L over here. Is that okay? Now, this is now my, what am I doing? My second harmonic, so we'll call it F2. And so this was 1/4 of C over L. And this one is 3/4. Can you see that? So it's 3/4 of C over L. So is it fair to say that the second harmonic is 3 times the first harmonic? Yeah? Okay. We are going to do one more. Oh no. Oh well, yeah, look. Okay. So here's the third harmonic. Now a lot of this is done already, so I won't rub it out. So we've 1, 2, 3 nodes, and note that we have a node at the closed end. And then we have 1, 2, 3 antinodes, and again an antinode at the open end. So we're following the rules. Okay, I'll pop in my arrows here. So this is node to node, which is half a wavelength. This is node to node, which is half a wavelength. And then this is node to antinode. Oh, that went a bit funny. Which is 1/4 of a wavelength. So the length of this from top to bottom, you can see it here, half a wavelength plus half a wavelength plus 1/4 of a wavelength. Yeah? Again, you can do that on your calculator if you want. So you can use your calculator and type in 1/2 plus 1/2 plus 1/4, and it will give you 5/4. 5/4. Just don't forget to put the lambda back in. So that's what I have here. The length is 5 lambda over 4. I want to sub it in to this thing here, so I need to isolate lambda. So I want to isolate this, so I'm going to multiply by the 4 to get it to cancel. Multiply by the 4 over here. So 4L equals 5 lambda, and then divide by 5, and we get lambda is 4L over 5. Same maths. Now, I'm doing this slightly different, so I'm going to take this out. So now that I have that, I'm going to sub that in up here. So I get C equals F times lambda, which is 4L over 5. I want to try and isolate the F. I did that in pink, didn't I? So I'm going to multiply by 5 here, multiply by 5 here. So I get 5C equals F times 4L. Again, I want to isolate the F, so I'm going to divide by 4L, divide by 4L. Now, I'm on the third harmonic, so we call this F3, and that is 5/4 of C over L. Yeah? So if you remember, the first one was 1/4 of C over L. So the third harmonic is 5 times the first harmonic. Yeah? Okay, so I've proven something here. I've proven that the first harmonic is 1/4 of whatever C over L is. I've then proven that the second harmonic is 3 times that. And then the third harmonic is 5 times that. Okay? So what I have proven is that only odd harmonics are present in a pipe closed at one end. Okay, so do you remember when your man was setting up his frequencies and he had the fundamental frequency at 8.5, and then he doubled it to get the next one, and then he doubled it to get the next one, and so we'll stick with 8, it's easier. His fundamental frequency, or his first harmonic, was 8 hertz, and then when he was getting his second one, he went to 16 hertz, and then when he was getting his third one, he went back and he multiplied the 8 by 3, and that was 24 hertz, and so on. Okay, that was on a string. What I'm saying is that in a pipe closed at one end, you wouldn't be able to get that one. You'll only be able to get the odd harmonics. So you wouldn't be able to get F4, but you'd be able to get F5. Okay, and that's what I've just proven with the maths. Is that okay? Now, please go back and look at that maths again. Okay, now what I want you to do is, you can see there, mandatory experiment sound 1. So there is an experiment that we're going to do where we're going to set up a standing wave in a pipe closed at one end, and we're actually not trying to we're not trying to prove the harmonic thing. We're more just trying to find the fundamental frequency. But yeah, I'll show you that experiment. We actually use it to find the speed of sound in air, which is quite cool. But for today, what I want you to do is look at stationary waves in a pipe open at both ends. Okay? So in a pipe open at both ends, so that would be, just like this. At the open end, you need an antinode. At the open end, you need an antinode. So the fundamental frequency in a pipe open at both ends looks like that. It has one node and 2 antinodes. Yeah? That's your first harmonic for your fundamental frequency. Okay, now, this is better. So there's the first harmonic. 1 node, 2 antinodes. There's the second harmonic, 2 nodes, 3 antinodes. And there's the third harmonic. So what I would like you to do for these 3 pictures is the maths that I did for these pictures up here. And prove to me, is it the same situation here that only the odd harmonics are present? Or is it like the string where all the harmonics are present? I want you to mathematically prove it to me by doing the exact same maths I did up above, but for these 3 pictures. Okay, so that is your homework. Can I please just, I don't know if I said it because I sent your video after my operation last week and I wasn't thinking, but I haven't posted the homework because you guys haven't posted the homework. Now, so many of you haven't posted the homework that I'm starting to think I didn't ask you to. So I gave you this homework on Friday. What I want you to do is do the homework, and I want you to put it into, I want you to put it into your folders. We're going to Anna here. So in Anna's homework folder, I want you to put in the 27th of September. Is that what it was? Yeah, 27th of September. And I want you to just do it in your copy and take a picture and put it up there. Yeah? So I went through and like, I don't think anyone had it done. So then I started thinking, maybe I didn't ask you to do it. So can you do that for me, please? So that homework that you have done, can you put it up? Because I want to check it. And I have the solutions ready to go. So as soon as I see your work, I'll post the solutions. Okay? And then today's homework, I'll put it in here now in a second, is going to be doing your calculations for the first, second and third harmonics in a pipe, open at both ends, and telling me, is it all harmonics that are present or only odd harmonics that are present? Okay? And post that homework as well. And that is due, I think it's Friday I have you next, isn't it? So that's due for Friday. Alrighty. Okay, bye.